Alrighty, so so last we left off, from what I recall, is we were talking about. Let me share for context. We were talking about the issue where it's unclear how to parallelize across object graphs. So I think what we can spend today on, or at least start, is to kind of think through and define how to parallelize object graphs. Basically hypothesis, because hypothesis updater calls are per object graph. And to that point, make this bigger so it's visible. Okay. So to that point, this is evidence graph LM, and we have a hypothesis, and it has an update evidence call, and inside this update evidence call, it calls hypothesis updater, and it calls update hypothesis, and we notice it's per graph ID, so it's getting per graph ID. And the issue was, so that's the context for it. So one, does that sound like a reasonable place to try to resume and figure out what we remember?
Yeah, sounds good.
All right. We also, do you recall any of our grouping LMs discussion?
Yeah.
So I haven't made any progress on that. That's still there. Actually, let me switch my sharing mode so I can share the desktop instead. There we go. So yeah, so that's still a to do over here on the refactor stuff. I have not made progress, but yeah. So parallelized it. So one thing about I've noticed as I was peeking at this like in a few minutes before the meeting was, I mean, I guess we can trace up of where all this comes from. So update evidence takes in a graph, and so wherever that gets called is going to be here. So this is interesting. Right, so this is how it gets split up by graph ID, but there is yeah. So that looks promising.
Yeah. I mean, so I think we would definitely need to fit however the parallelization is happening, whether it's the CPU backend doing multi-threading there or the GPU doing it in like batched operations into the backend. So certainly it seems like this logic here that's going on in the evidence graph LM right now will need to be shifted to the backend. But is there an issue with anything about like kind of the current place in the code there? Like, I don't know, conceptually to separate into the backend, are there parts of this that the backend shouldn't be aware of?
I mean, I don't
It doesn't seem like
I don't see anything, because it's like we either scatter here and then gather here. Oh no, this is where we haven't even defined it. So yeah, so if we use multi-threading, scatter, gather. Okay.
Well, the thing, if we're talking about kind of like LM groups, ideally we would want every LM to do the scatter before doing a gather, so that we could use different CUDA streams to parallelize even across LMs. I think within an LM, doing it across the object graphs is similar to the implementation I have right now. But figuring out, I think it's a bigger code rehaul to have the scatter come before they gather for all LMs at one time step.
Well, I mean, we can explore that, right? Like we can see, we can do a kind of don't chase that down. So this is update possible matches. I'm not seeing any references in this file, so this is
So that gets
probably
called in graphlm.compute possible matches. I have a little
right here.
spec that I just did earlier. Yeah.
This one, right?
Mm-hmm. So that's
I mean,
for
this
per
is
learning module.
okay. There we go. Yeah, I was like, okay, so it's per learning module. So compute possible matches.
And then I think above that, it's the matching step function, also in GraphLM.
Yeah, up here. Okay. It's still per learning module. Yeah, we just have to just turn this interface inside out, basically.
Yeah.
So right now we're telling the learning module do these steps, and instead we're gonna do these steps with the learning modules, right? That's the entire refactor. Okay.
Yeah. And so it's, Monty for graph matching step learning modules is where it actually iterates over the learning modules. So I think that's where we would want to switch to like a non-blocking scatter for every LM, and then a gather for every LM.
Hit Monty for graph matching. Oh.
Unless something's changed. This is from the code a few weeks ago.
There we go. Right. Okay.
Yeah.
Yeah, so this is what's gonna get. So yeah, so instead of for this, I mean, yeah, that makes it seem. I mean, it feels like it should make no difference because like the logic is still at this level. So whether we do it for here or whether I'm just thinking at the logic is at this level of abstraction either way. We either do in a for loop and call specific methods, or we can call the specific methods and pass in the set. Like it should be the same thing. Okay.
And pass in the set. Yes. So like you're saying if we had
a collection of all LMs to do the steps.
And pass that into like the backend object basically. So it would be like this Monty for graph matching references the like hypothesis updater that can operate on all LMs at once. Because like right now, it's Monty for graph matching isn't aware of the hypothesis updater. It just has a list of LMs.
Well, right. I don't think. Yeah, I hear you. I'm thinking. I don't want to go directly to hypothesis updater because that's like like internal guts of learning module.
Mm-hmm.
I'm just trying to figure out how to represent it so it's accessible, but it's still.
Yeah, so if we didn't want to expose the internals of the learning module sort of backend or hypothesis updater to this Monty for graph matching class, I think we could still leave it inside the learning modules, but that's where we would have to iterate over every LM and dispatch the work. And then outside of that loop in the next step, iterate and collect. So do the scatter and gather in two different loops.
Well, what information do we need? I guess what I'm trying to figure out is like what info do we need to expose from a learning module to get to be able to do parallel compute here with a GPU backend, right? Oh wow, this is not gonna wrap for me. Okay, I need to wrap it. Okay, so like I guess what I'm trying to think is like, okay, there is if instead of we want to do instead of do this, we want to have some function, right? That will. So what are we doing? For if sensors input, so we're gonna so like this is a weird way. This is kind of a calling a per learning module function, right?
Mm-hmm.
And so what I'm saying is we should be able to do, instead of doing that, we should totally be able to just do this, right? Something
Mm-hmm.
like that, right? Although this would be like, for all LMs or something like that there, right? Like how do we avoid the for loop, right? So the first thing I'm seeing is we would need something like this, and then LM step method. Okay, and this is called per learning module. So there's some so this is like self step learning modules, and it's against self learning modules.
Mm-hmm.
That's the next step. This sort of does. So here, let's do this. This ought to be replaced with that. I mean, ought to be able to. So this should be able to be replaced with something like that, right? And still sensory inputs. So still sensory inputs for all LMs. And this starts to smell like the same function, really, because it's got the same signature. There's
Yeah.
almost no reason to break it down, right?
Yeah,
Because
what is the difference between set stepwise targets and then calling the step method?
Let's find out. Set the stepwise target for each language, i.e. the class label of the object that is actually receiving sensor input from. Oh, this is an experiment. This is baked. This is some baked-in experimental framework.
Hmm.
So we could just yeah, I don't know how important. Yeah, this is an issue with the coupled experiment and the actual Monty framework thing. So let's design it without the coupling first. So going back would be. So this is set stepwise targets is experimental experiment method versus this is the actual runtime method.
Mm-hmm.
I'm gonna say runtime for the Monty system and experiment for experiment specific operations that are doing stuff, right? So this would be like an experiment method. This is a runtime method, and so we can see that. I mean, this at processing. Yeah. So this is basically this, right? Step learning modules. Well, I'll just call. I mean, technically, we can maybe do it like it's a step type there, just to be clear. Self-step type learning modules, because they have matching step or evaluation step, but kind of doesn't matter for the purpose of what we're thinking about here. So that's parallelized. Over here, it just skips. Yeah, so if the sensor input is none, there's nothing to do.
Yeah.
So this could be like a no up.
Yeah, and that could be a part of the function that we're calling there. Like, if it doesn't have to be handled in this function.
Yeah, I mean, I'm just marking a no up. It's like in case that we don't want to have this branch, then maybe something. Does that make sense?
Yeah.
Well, so now that I said that, this is per LM. So that means the whole thing is actually just this. So this function. So in my mind, there is an experiment method that sets stepwise target for everything, and there is a runtime method that executes the step side, which is kind of true. That's what step learning modules should do.
Mhm.
And there is a with a note that note step might be no up if sensory input is none. Okay, there. So this is parallelizable. So and then so how do we get here? Because we were seeing, so this calls, we weren't here. How did we get up here? Because you brought this up, but we were somewhere
This
deeper
was
in the stack.
to get, yeah, and this was just to get to the level where
Okay.
you're iterating over LMs. Everything else was a per LM call.
Okay, cool. So let's look at the matching steps and learning steps. So these will be methods on the learning module. So it's matching.
So,
yeah.
So in that step learning modules, we're now switching to, instead of doing the for loop in that call, we want to call directly into this set stepwise targets or the actual like matching step or exploratory step. But we still have to either do the for loop there in that step, or like, sorry, in that function, which would still be a part of this Monty for graph matching, or we have to switch to find a way to like dispatch all LM data to some sort of backend, which we didn't really want to do. So right now we're shifting the for loop iteration to this other method. Is that okay with, is that like kind of what you would like to see? Because I think we still have to do some level of this. Maybe it doesn't have to be explicitly a for loop in the code, right? But we still have to have, you dispatch all the work across LMs and then wait for that to be done and then collect all the data from the LMs. And that needs to happen at this level before we get to the per LM level.
So one of the things I want to get to is, so we talked about update possible matches here, and we do use multi-threading here, right? And so it's like, but because this method is on the single learning module, then the maximum parallelization we can get is per graph ID in a learning module, right? But what we're trying to get to is how can we parallelize across a bunch of graph IDs and learning modules? Like
we want to parallelize across all learning modules.
Right. And so right here is a constraint that what I guess what I'm trying to imagine what the API looks like. And so yeah, the joy of live design. So I guess I think the problem in my head is I'm looking at is, here is a for loop. Anytime we have a for loop like this, we can parallelize it by passing a set. And at a certain point, and as long as the API, I guess what I'm saying is, if we look at the current implementation and we see a for loop that iterates through a list, then we have restricted that is a restriction of how much can be parallelized. Because now I just said I can't, because this method is called for every learning module, then I for sure have to have a for loop somewhere for every learning module to call this method. I can't say call this one in parallel for every learning module, right? So it's sort of like, because this parallelizes, this for loop can be parallelized across graph IDs, but this method is not yet parallelizable across LMs.
Yeah.
So I'm trying to link it up with here, where it's like this method is parallelizable across LMs, and I'm trying to get them to meet, so that the interface of these, like, so I want to go up from here and down from here and see if I can meet them while maintaining the parallel interface.
I think it's still like the mechanism of how they're being parallelized still matters, because when you want to call it on a set of learning modules instead of a for loop, how, like right now, like this Monty for graph matching just can directly interface with every learning module separately. But if we want to run those learning modules as a set, how do we represent that? Because that's where we would need sort of like one runtime to handle that logic of setting up all the data for the inputs to the LMs, running them in a batch. So that would kind of change the dispatch structure to now be having some representation of multiple LM dispatch, whether that's a hypothesis updater or some new class that runs them all in parallel. Because I just don't see a way that we can just like run these steps for all learning modules in parallel and just have this Monty for graph matching only reference those learning modules and not have some other sort of collection parallelization object that tracks that, unless we still do a for loop approach, but we do the non-blocking case that we were kind of talking about last time, where you can still iterate over each learning module, but you just need to make sure that each iteration of that loop doesn't wait for the work to finish.
Right.
It just dispatches the work. And so then that for loop will end before any of the work's complete. It's just dispatched it across all LMs. And then you have another for loop that, or you don't, probably not a for loop, but
this thing. I mean, you're just gonna literally do this in the abstract.
Yeah, but that's because you're actually multi-threading would be different than GPU dispatch here, because we can split the CPU process to do multi-threading. Whereas like we still want one CPU process launching all of this work on one GPU. So I think the for loop approach would be fine. We would just need to shift it so that instead of doing all the work in one call to the LM, we switch it to you have like a dispatch call, and then you have a sort of like waiting call and like a collection call. So like scatter, block, gather.
Yeah.
Does that make any sense?
I think so. Do you have something in mind? I don't have anything to type. I'm still thinking through what you're saying. If you have something to type, let me know. I'll give you the screen or take the screen. I'll just.
So we're looking, update possible matches there. I think we would want to go back to the higher level, like the step learning modules.
Right.
So like that for loop iterating over the learning modules. I think we want that to do dispatch the work for each learning module in that loop. I actually already had some of this written down in that function. So yeah, we would have the dispatch step.
Are you sharing a screen or something?
No, I'm just looking over my notes.
Oh, okay.
And then we'd have to have some. What I have was still having the Monty for graph matching have a reference to the backend so that it can call, like we'd have a single backend that's shared between all learning modules.
Yeah, so we have something like self backend.
Yeah, and it should have like a wait until complete call, something to let the.
Yeah. So what's the so what's the API of the backend that you have in mind? So it's like join would be the join all of them. If we just use the multi-threading, or is there a GPU term?
This just needs. We need to have some call to just wait for the work to complete.
Yeah.
And
join. Okay, and then how do you?
Then we can process all the results however we want. It just kind of depends on the downstream how we'd like to handle the results of the LM update steps. But at that point, we're kind of done with the hypothesis update or parallelization.
Okay.
So like at that point, if we want to loop through the learning modules and like, call some downstream effects, or if we just want this function to return out.
So what's the high level algorithm here? What comes before the join?
So yeah, we have, okay, so yeah, so that, sorry, so yeah, if we're getting rid of that for loop, then yeah, it would just be like, yeah, dispatch, join, process results, like 3 steps.
So there'd be learning modules, sensory inputs for LLMs, and then we would just join all of these guys. I mean, it's not even at that point.
It doesn't need,
yeah.
like the backend should be able to track whether it's done with all of the work.
Okay. And then I guess dispatch something, right? There's like a method here, like a function to run. Or is this the?
So the backends, because it's going to
be this.
It'll define. I guess I don't know exactly because this is where we'd have support for different backends like CPU
Right.
and GPU. So like they would be aware of, like they would actually have to have different implementations of the fundamental operations going on. So we couldn't just pass in a function and have them run that. It would have to be like they know what the functions are and we're just calling into them.
Okay.
But yeah, there's still several points in the current stack chain through the learning module. So I don't know exactly how we want to refactor that.
Okay. But does this sound, so then it sounds like, we have a backend, that's the abstraction, and then it's going to step all the learning modules. And then, quote unquote, the default backend would be this.
Yeah.
Right. And then versus a GPU backend would do something else. So what would the GPU backend do?
So this kind of depends on how we define like the LM groupings and everything. If right now we're just saying each LM is its own group, or kind of ignoring that change, then it's going to do a different CUDA stream for every learning module and dispatch the work.
So consider grouping of in the learning modules call below, right?
Yeah. So if we wanted to do a grouping, we would want to iterate over those groups here and do a different. Yeah. But whatever that grouping is, we would have the backend would basically run a different CUDA stream for each group. And then in that join step, it has to wait for all of those CUDA streams to finish before processing the, giving you back the results, however you want to do something.
Okay, so it's like, so for group and groups, this is the CUDA backend. So for group, pseudocoding here. So for group and groups,
we just would like dispatch the work, some sort of dispatch stuff. And then the CUDA backend join has to happen once that for loop's done. It has to be outside that for loop.
Yeah, so this, I mean, this is just that.
Yeah.
Right. Okay. All right.
Is that making sense?
I think so. For group, so we do that. And then when we aside there, okay. Yeah, gotcha. Yeah, I mean, so then do we need anything else to collect for the CUDA backend dispatch? So what we're talking about here is actually running this step, right? Like, so we still, it's, this needs to be like a matching step. Let's see, graph learning. don't care about tests. So okay, so we have, where is it? There. GraphLM, cool.
Yeah, I can, because I traced this earlier, trying to send in the chat just like the list of function calls.
Okay. That contributes to send messages. Yeah, okay.
Very legible in the chat window.
Okay, cool. So that's the trace here. Graph matching site computer bus. Okay. So in matching step, okay, but it's an observations. So this needs to get rewritten because it's a learning module thing. Right, so it's all, so there's gonna be a CUDA backend matching step, learning module matching step. It's gonna take learning modules and whatever, right? That's how the translation would likely go. That's what I'm trying to think through. So dispatch, but in there, that just means CUDA backend. So this is matching step for the group. Yeah, just essentially have to expose all the algorithm. Then we have, there we go. All right, so this is compute possible matches. It's gonna do a bunch of stuff. It's gonna be, oh wow, it's on the same. Okay, I was like, why am I getting? It's the same file. Got it. I was like confusing myself there. There we go. All right. So we have. There we go. So we're here. So we'll come back to it. All right. So we have matching step, and there is a compute possible matches per group. Oh, I lost my sensory data somewhere already. Or right? Wait, this is inside. Matching step, observations. There we go. Okay, so okay, this is, oh no, there it is right there. So group, sensory inputs. And then, like you said, and then we're gonna do even more. Compute possible matches. And then update. Okay, but at this point, it's just okay. So I mean, I think I understand now. So it needs to be the. It just needs to. So at a high level. Okay, let me just see if I'm tracking what you're saying. So whether it is grouping or not, the point being is there's a backend, and the backend, instead of doing a for loop, it's gonna be just get all the learning modules and all the sensory inputs. And if it's a default backend, it's just gonna do a for loop and do whatever it's doing today. If it's a CUDA backend, it's actually going to implement these other methods, which, so does that mean, okay, but okay. So, okay, this is straightforward, but now, like, how does this code get organized? Because, so what this means to me is that if we have, so any method that we flip inside out means that the learning module there's like two implementations, and they're different, right? One of them is a method on the learning module. The other one, the learning module, is a data passed into the thing and needs to
So
expose.
I think, like in the kind of proof of concept code that I have, the backend is really just implementing the actual hypothesis updater operations, and isn't trying to handle as much of the logic around the LM itself.
Right.
And so, yeah, I think there's kind of two directions. We either have this CUDA backend have to handle a lot more of the LM logic if we're calling directly into it at this stage, or we maintain that it's still kind of per LM that they handle their own sort of logic, but it's just that we make sure that none of those calls into that LM through, like, matching step, compute possible matches, update possible matches, update hypotheses, none of those wait for the work to be done. They all just dispatch the work and then return, so that from this high-level step learning modules method, we can call into every LM and have it dispatch its own work, but all those calls return, so that then we can wait for all that work to be done in parallel. So like each LM will still reference that single backend, and it can still do the work in parallel, but the dispatching kind of control logic comes from the LMs themselves. Or we switch to trying to have this sort of more involved backend class that can keep track of some of the different settings per LM. Or...
I think I finally understand what you've been trying to say.
Okay.
Got it. Yeah, so basically what you're saying is, like, with a CUDA backend, what we could do is retain all this logic, and as long as by the time we get to here, as long as it's not actually doing a compute, but just queues a
Yeah, just queues it. Yeah.
patches it, queues it up for later, whatever, it can still execute the exact same for loop, whatever. We just need to find the right place to come back and then be like, okay, join, and now resume the other. Okay, got it.
Yeah, so like in my little code that I wrote before our last meeting, it kept that same for loop that we have there in the code. And yeah, just change it to, instead it's just a dispatch instead of a compute call. And then once that for loop completes, then we have the call to like wait on the backend to finish and then process results. But we still require changing each of these functions along the way to make sure that it is just dispatching and not waiting for the results. But it wouldn't require as much code rewriting of like what the backend is doing versus what the LMs are doing.
Yeah. So we would have to, audit this thing to see where the previous results are being used, right? Because you cannot proceed past the join, past the gather in this for loop, right? Or can you set up the computation even with like a follow-on computation? Like if I like let's say this is made up, but like, I have two calls in a sequence, and let's say this call uses the results from this call. Will a CUDA backend have no problem setting that up?
Yeah, so I think what we would do, this is where we need to have really good, clear sense of what the sequence of operations could be. But the LM, we could set it up such that the backend object LM interaction, like it's aware of the pipeline of operations. So we can kind of do one dispatch of that full pipeline. So we don't have to control kind of each step of the pipeline, dispatching and queuing and waiting in this level of code. We can just be like, dispatch this whole pipeline of operations and run parallel for each of them.
And so that's what I'm saying. So like, yeah. So let's find an example of an LM that does this. I'm slowly catching up. So thank you.
Yeah, no, it's kind of a weird programming paradigm to think.
Yeah, but I think like like you flip the switch. I get it now. So now the specific question. What are we talking about? Update evidence. Update evidence. Okay, so Yeah, blah, 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 query, and the query has been select features to use, get current displays. Okay. Is this expensive? Did you replace one of these?
No, I only
No? Okay.
replace the hypothesis updater like
Oh, right.
operations themselves.
Okay. So update evidence and update evidence. Oh, there we go, right there. Okay, cool. Blah, 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 and then hypothesis update. Okay, got it. So, okay. And so basically this would switch to become something like, we wouldn't have this equals yet. We would just have self hypothesis. It would basically be, the interfaces would just have to change to something like this, right? Where it's just, wow, thanks cursor. Okay, it's like overriding tab is, like tab is a useful thing. Okay, so it'd be something, like this is essentially, this is the dispatch.
Yeah.
And then it would be, then you get the results. No, then we have to stop. Then we have to stop here. And then later on, there's like an entire call, different call, update evidence, and it's like process evidence or something, right? Like after the.
Yeah, so we wouldn't have it stop. We would just have it return, right? Because we want that higher level for loop to finish each of these dispatches.
Yeah, so we gotta find these breakpoints where it's like we need to split a method into the before the dispatch and then after the join, right? Before the scatter, after the gather. What terminology you use in CUDA? Because I keep on making it up. I've like scatter, gather, map reduce, fork join.
Yeah, I think you can do a lot of things. I think it's helpful to just think of like dispatch operations, and then like block or wait for those to complete.
Okay, cool. So
like non-blocking versus blocking.
Got it. So we gotta evaluate the functions and see which portions are dispatch, and then everywhere we need to block, we need to essentially create a new function. Like we need to split up functions at the block points. Yes? Am I saying the same thing?
Well, unless it depends on what we want to include in sort of the pipeline of operations the backend's completing.
Got it.
Because we could still just, you could have that one dispatch and have that queue off, for that LM, kind of all of the hypothesis updating steps.
Yep.
And not have to mess with keeping track of that at the evidence graph LM level.
Yep.
So I think, kind of ideally, like whatever step this is running in the experiment, we just have one dispatch call, one blocking wait call, and then we take the results and like continue with the next steps, right? Like doing LM voting and tallying and goal states and all that. But all of the evidence update operations occur from this one dispatch to the backend pipeline.
Got it. Okay. This smells a lot like initially at first approximation. It smells like a visitor pattern. Like I want to pass it a visitor. Like each one of these things pass a visitor, and then here be visitor, dispatch or whatnot. So I guess let me say it differently. Again, thinking out loud and raw. If we split it up, how do my CPU stuff works? How does my CPU stuff works? It's almost like I do like, yeah, I guess I'm just trying to figure out what is the common interface between that paradigm and this and the current paradigm. And like visitor kind of smells like maybe that's like adjacent to the right interface, because if I each one of these calls a specific method on a visitor, and if it's like the CUDA visitor, it's gonna just queue that dispatch the stuff. But if it's I'm just trying to mention, but if it's a CPU visitor, it's like then I guess it needs to immediately return some, like, I don't know how to design that. And maybe visitor is not the right one, but that's what I reached for immediately here.
Yeah, I haven't thought through the CPU side as much.
Yeah. Like how do we both?
Right. So I mean, like a simple kind of naive CPU backend, certainly for one kind of conceptualizing one step, this would work. I'm trying to extend that to doing these sort of pipeline of steps. I mean, you could have it do multi-threading, or you could just have it do the full for loop and actually wait for each step to complete. But that kind of already changes the interface because you wouldn't have this dispatch wait process results call like the CPU doesn't if it's operating sequentially.
So I guess, okay, I guess the CPU backend, I mean, it's just, it would calculate it immediately, but I would just have to just do a level of indirection, right? So if so if I have so everything would have to be designed to support the CUDA kind of dispatch and a block.
Mm-hmm.
And the way this, I think I'm now catching up how the CPU one would work is in a CPU visitor when I dispatch it, or since everything is the same API, maybe don't need a visitor anymore. It's just the API. So when a CPU does it, it just stores the results in the variables in its backend, and then when you call the things up the block, it just reads it from where it's stored. It just reads it from its internal state. Versus like on a CUDA, okay, got it. So a CPU backend, when you would dispatch to it, it would actually do the computations right there and then, and it would store the results in its internal variables. Versus for a CUDA dispatch, it would start queuing things up to send off to the GPU. And then when the CPU backend blocks, there's like no up, like all the results are already there.
Mm-hmm.
Versus CUDA blocks, we actually then wait for the GPU to finish, and then we resume everything, and the results are there either way. Like in the CPU, we block was a null up, and the results were already there, so we proceed, and the slope was the dispatch code, and in the CUDA part, block actually calculates the results and gets them back, and we proceed as well. Does that sound?
Yeah, actually, I think that makes sense because we could probably even switch the blocking call just to be a part of the very beginning of the GPU's process results. We don't even have to have the blocking be made available at this level. So it could just be dispatch work, process results. And the CPU just does that sequentially and then has them all ready, and the GPU does a dispatch them all, run in parallel. And then whenever you want the results, it first waits for the results to be done and then provides them back to you. And that's actually reasonably more in line with how GPU programming typically works. Like typical GPU programming, right, is it's like you have a CPU thread. Whenever you want to run something on a GPU, you dispatch the work, and then it'll just kind of automatically handle this sort of like blocking stuff. It's just as soon as you actually want to process some of those results, that's when it'll wait. So like as long as you do other things in the meantime before you process the results, it'll handle all of that running in the background. And then as soon as you want the results, that's when the CPU thread will then be stuck waiting for the GPU to finish.
Got it.
So we just want to do the same thing.
Okay, so let me write up the GPU version. So backend block for results to come back from GPU, process results. And then GPU backend is dispatch work to GPU. Yes? No? And then return immediately. Immediately. And then it's like, so in the CPU version, it would be do the work, return after work is done. And then I guess store results and turn. And
yeah, I think this is where we can still kind of make a choice about what we want to be handled by the LMs themselves and what by the backend.
Yep.
Because if we still have it be that like the LMs are kind of have their own functions to set up and then dispatch this work, we can then still store the results in those LMs.
Okay, yeah.
Without it being stored and handled by the backend.
I thought somewhere.
Yeah.
For later retrieval. So it's like could be backend intermediate vars
Mhm.
could be learning modules, etc. Okay. Return after work is done. CPU backend results are available, so process results right away. Okay, this is promising. Let me
Mhm.
put this in chat so it doesn't disappear. So you can also see this.
Yeah.
As we coming close on time. Okay. So we have like 4 minutes. So perfect. Done.
Yeah.
This is great. So I guess what I can do is I can write up my I guess I'll just post this in our discourse
Mhm.
here.
Mhm.
I can just post this in the discourse summary of like this is the high level thing, and I'll kind of think through what to update about. Well, actually, so we made progress. I think we still need to get the details, but I think we have the high
Mhm.
level one, right?
Mhm.
Does that sound right? Okay, so I think so. I'll report over here, say that we do have a high level thing. I will try to describe it. Please correct me if I screw that up or whatever. And then for the next time will be to see if we can push it down the details farther.
Mhm.
But this has been
Yeah.
super helpful. Like, and thanks
Mhm.
for repeating this paradigm over and over again until I got it.
No problem.
It'll be
And
I'll try to describe it in my words as well for anybody who comes after. Let me see to do.
yeah, and I could try to think through and make sure that this sort of high level plan I think would work with like conceptualization of the GPU backend and see if there's any problems I haven't thought through. And I guess, yeah, we just want to make sure that how we're considering it now, and I think it would work both for an individual LM or for like an LM group if we wanted to shift to that architecture in the future.
Will this work for both individual LMs and groups of LMs? Yeah, perfect. And then the other thing I want to do is just like I need to find the process results points that might block, or like, does that make sense?
Mm-hmm.
To do that's one. And I'm just writing the notes here, but I'll summarize it again in the discourse. Okay.
And this is a detail we don't have to, I think about right now, but I do want to mention it just because it could impact sort of how we think through the high level architecture.
Okay.
Traditionally, one of the most common bottlenecks for any heterogeneous programming where you're doing CPU and GPU like this is going to be transferring data between the CPU and GPU. That's often much more of a bottleneck than the actual compute running on the GPU. So the best way around that is we try to keep as much data resident on the GPU as possible. And I think it's conceptually very feasible because the Monty experiment, like it's not like it really cares about a lot of those intermediate data steps, like all the intermediate formats and like, the output of one GPU kernel into the next. But it would basically just mean that anytime the LM does need to access its own internal data, right? Like look at an object graph or something, it might have to read that from the GPU instead of just having that already in CPU memory, which is like pretty easy to do. It's just like conceptually we want to make sure that this architecture works where we could keep as much of the data on a GPU as possible and prevent having to do these big data transfers and like kind of just read back and forth like the new inputs, whatever changes happen, and like the outputs at the end.
Gotcha. Okay. Good to know. All right, I'll write up the note summary. Let's stop here.
Cool.
And we'll catch up in a few weeks on when you get back and go from there.
Yeah, sounds good.
Okay, awesome. Thanks, appreciate it. Good to see you again.
Tristan.
Feels like progress. All right.
Exciting for sure. Yeah.
All right. Cheers.